This is a video for AQA Mechanics. It's Impulse and Momentum section 2.2, where we're looking at the loss of energy due to impacts. We've already considered impacts and how in an impact the momentum is conserved. However, it's unusual for energy to be conserved, so that what we want to do now is to consider how much energy is lost in an impact. If E equals 1, then the collision we say is perfectly elastic, and then there will be no loss of kinetic energy. So if E equals 1, we have both conservation of momentum and conservation of energy. However, more often than not, E is not going to be equal to 1 and will lie somewhere between 0 and 1. So the amount of energy lost will depend on the value of E, the more energy being lost for smaller values of E. We need to consider the change in the kinetic energy of both of the objects in the collision. Of course, change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy, where kinetic energy is half mv squared. So now kinetic energy is a scalar quantity, so a negative value of this will indicate a loss. I now want to consider a couple of examples of this where we're calculating the actual loss in kinetic energy in some particular collisions. So first of all, we have one here where we've got the before and after situation. So before, we've got a 6 kilogram mass moving towards a 1 kilogram mass. The 1 kilogram is at rest and the 6 kilograms moving at 4 meters per second. And afterwards they move off at 6 meters per second for the 1 kilogram mass and 3 meters per second for the 6 kilogram mass. So if we want to consider the actual change in the kinetic energy, we'd have that the change in kinetic energy is equal to 1/2 mv1 squared plus 1/2 mv2 squared. So that's the kinetic energy after the impact minus 1/2 mu1 squared plus 1/2 mu2 squared. So there should be indices on the masses there as well, m1 and m2, m1 and m2. So we've got the total energy after the impact minus the energy before the impact. Now if we calculate that for this particular situation, we see that we've got a half multiplied by 6 multiplied by 3 squared plus 1/2 multiplied by 1 multiplied by 6 squared, and then minus 1/2 multiplied by 6 multiplied by 4 squared, plus of course 0 for the mass which is at rest. Now if we calculate that, we get negative 3 joules. In other words, a loss of 3 joules energy in that collision. In the second example, we're asked to find the change in kinetic energy when we have two particles that coalesce. So we can say, well, after the collision, then we have both particles moving together at some velocity v. So conservation of momentum would tell us that the momentum before the impact, which is 3 multiplied by 4, and then plus 2 multiplied by negative 4, is equal to the momentum after impact, which is the total mass of 3 plus 2 multiplied by v. If we calculate that, we find that V is equal to 0.8 meters per second. So therefore the change in the kinetic energy, again given by a half mv squared minus a half mu squared for both particles, so the total energy after the impact is going to be a half multiplied by 5 multiplied by 0.8 squared, and then the energy after impact is 1/2 multiplied by 3 multiplied by 4 squared, and plus 1/2 multiplied by 2 multiplied by 4 squared. And if you calculate that, you get negative 38.4 joules. So a loss of energy, this time of 38.4 joules. So in collisions then we have momentum is conserved, but energy is definitely not conserved, so there will always be a change in the energy unless we have perfectly elastic collisions. That's the end of this particular video then, and in the next video we'll be looking at what happens when we have successive impacts of spheres. So one collision followed by another collision.